There are roughly 80 million redheads on Earth right now, and by every rule of natural selection, that number should be 0. Think about that for a moment, not as a curiosity, not as a fun fact to file away somewhere. Think about it the way an evolutionary biologist would, staring at a spreadsheet of survival pressures and genetic drift, watching a trait that should have vanished long ago still stubbornly, quietly, beautifully persisting. 80 million people walking around with copper hair and pale skin, and in many cases, a peculiar relationship with pain and anesthesia and sunlight. People who carry a mutation that reduces the body's ability to produce one type of pigment in favor of another. A mutation that, by most measures, costs more than it gives. And yet here they are. Here they have always been. That is the question we are going to sit with tonight, in the dark, in the quiet, in the archive where the stranger files are kept. Not just why redheads exist, but what their existence tells us about the hidden logic of evolution, about the deep past of our species, about the ancient migrations and isolated populations and forgotten pressures that shape the people alive on this planet right now. Because the story of red hair is not really about hair at all. It is about survival in impossible climates, about the strange mathematics of recessive genes, about prehistoric populations that shrank to almost nothing and then exploded outward, carrying their mutations with them like seeds scattered by a wind that blew across tens of thousands of years. It is about what it means for a trait to persist, not because it is useful, but because it is attached to something else that is, and it is about what it means to be. In the language of population genetics, a genetic ghost, a living echo of a world that no longer exists. Before we go any further into this archive, if you find yourself drawn to the kind of history that hides beneath the surface of what we think we know, consider subscribing to the channel. These are the files that don't make it into textbooks. And if you're listening right now, in the dark somewhere, I want to know where. Drop a comment telling me what time it is and where you are in the world. There is something quietly remarkable about the idea of people across every time zone settling into this same darkness, drawn to the same ancient question. Now, let the light stay low, and let's go deeper. To understand why redheads shouldn't exist, you first need to understand something about how evolution actually works. Not the simplified version we learn early on, where useful traits spread and harmful ones vanish. That version is true as far as it goes, but it misses most of the complexity. Evolution is not a careful engineer. It is more like a river, finding its path through the landscape of possibility, constrained by what already exists, shaped by forces that have nothing to do with what would be optimal. And sometimes a trait persists not because it is good or bad, but because it is tangled up with something else, because it hitches a ride, because the forces that should eliminate it are weaker than we assume, or because it offers advantages in specific circumstances that are easy to overlook when you are only looking at the whole. The textbook version of natural selection is almost too clean. A mutation appears. If it helps the organism survive and reproduce, it spreads. If it hurts, it disappears. If it does neither, it drifts, randomly rising or falling in frequency until it either fixes itself in the population or vanishes entirely. This framework is not wrong. It is just radically incomplete, because real evolution happens in environments that are constantly changing, in populations that are constantly moving, in genomes that are not collections of independent genes, but tangled webs of interacting sequences where changing one thing changes many others. The river metaphor is useful here. A river does not flow in a straight line toward the sea because that would be optimal. It flows wherever the landscape allows, bending around obstacles, pooling in low places, carving channels that persist long after the original forces that created them have changed. Evolution is like that. It works with what the landscape gives it. Red hair comes from a mutation in a gene called MC1R. You can say it as letters, or you can say its full name, the melanocortin-1 receptor gene. But what matters is what it does. MC1R is responsible for regulating the type of melanin your body produces. Melanin is the pigment that colors your skin and hair and eyes, and it comes in two main forms: eumelanin, which is dark brown or black, and pheomelanin, which is red or yellow. Most people produce predominantly eumelanin. People with red hair produce predominantly pheomelanin because their MC1R gene is not functioning in the typical way. The mutation disrupts the receptor's ability to signal the body toward eumelanin production, and pheomelanin fills the gap. This is not a dramatic, catastrophic mutation. It is subtle, a single letter change in the genetic code, or sometimes a few changes in a gene that sits on chromosome 16. But the consequences ripple outward in ways that are surprisingly wide-ranging, which is part of what makes the Redhead story so strange and so worth examining. Because MC1R does not only influence hair color, it is involved in pain perception, in inflammation responses, in how the skin reacts to ultraviolet radiation, in how the body responds to certain anesthetic drugs. A single mutation in a single gene, and the effects touch nearly every system that interacts with the outside world. Think about what it means for a single point of genetic code, a single substitution among the 3 billion base pairs that make up the human genome, to have effects that reach from the follicles of the scalp to the nerve endings of the skin, to the way the brain processes the signal of a scalpel cutting through tissue. The genome is not a list of independent instructions. It is a network, densely interconnected, where one node can influence dozens of others in ways that are still being mapped. MC1R is one of those nodes, and its position in the network, its connections to ancient signaling pathways that predate the evolution of mammals, is what makes it so consequential. The mutation is recessive. This is crucial. To have red hair, you generally need to inherit a variant of MC1R from both parents. One copy is not enough. If you inherit one variant and one typical copy, you will probably have dark or brown hair, though you might have slightly warmer tones, or freckles, or a sensitivity to sun that hints at what is hiding in your genome. 2 copies and the pheomelanin wins. The hair turns red, the skin turns pale, the freckles emerge, and a whole constellation of associated traits comes with them. The recessive nature of the gene is part of why it persists. A recessive mutation can hide for generations in carriers who never express it, invisible to natural selection, protected from elimination by the simple fact that it is not being expressed. 2 people with no red hair can carry the MC1R variant and pass it to their children without ever knowing it was there. The gene moves through populations like a rumor, whispered but never spoken aloud, until two carriers find each other and the secret surfaces in the next generation. Imagine a family where no one has had red hair for 3 generations, perhaps 4. And then a child is born with copper curls and pale freckled skin. And the parents look at each other with something between surprise and recognition. The gene was always there. It was simply waiting. But hiding is not the whole story. Recessive genes that are truly harmful still disappear over time, because even if they hide in carriers, the carriers who happen to express them suffer enough that the gene's frequency slowly declines. The fact that MC1R variants have maintained a frequency of roughly 1 to 2% in the global population, high enough to produce red hair in about 1% of people worldwide, suggests that something is keeping it there. Something is balancing the scales. To find that something, we need to go back. Much further back than the medieval associations with witchcraft. Further back than the ancient Greek and Roman observations about flame-haired barbarians from the north. Further back even than the earliest written records. We need to go back to a time when the ancestors of modern Europeans were moving through a landscape that was nothing like the world we know, into a light that was nothing like the light they had evolved under, and finding that certain mutations that had been quietly accumulating in their genomes for thousands of years suddenly became very useful indeed. The story begins in Africa. Almost all human evolution begins in Africa, because that is where our species spent most of its existence. For the vast majority of the 200,000 years or so that anatomically modern humans have existed, we were African. We evolved under African sun, with African UV levels, with the kind of intense, year-round solar radiation that makes dark skin not just useful, but essential. Eumelanin is a remarkably effective sunscreen. It absorbs ultraviolet radiation before it can damage DNA, before it can destroy the folate that is essential for fetal development, before it can cause the cellular damage that leads to skin cancer. Dark skin in high UV environments is not an aesthetic preference. It is a survival tool, refined over millions of years of primate evolution under equatorial light. Imagine standing at the equator at midday. The sun is directly overhead. The UV index is at its peak. In that environment, every layer of melanin in the skin is doing work, absorbing radiation, protecting the delicate machinery of the cells beneath. A person with deeply pigmented skin can stand in that light for hours and suffer relatively little damage. A person without that protection burns within minutes. In the environment where our species spent its formative hundreds of thousands of years, dark skin was not one option among many. It was the baseline. It was what survival looked like. But then, somewhere between 60 and 80,000 years ago, a relatively small group of humans left Africa. They moved north and east, following coastlines and river valleys, spreading into environments that were radically different from the ones their ancestors had known. And as they moved further from the equator, they encountered something their genomes were not prepared for. Less sun, much less sun, seasonal darkness, winters where the sky was grey for months at a time, and the angle of the sun was so low that even on clear days, the UV radiation reaching the ground was a fraction of what their ancestors had evolved under. This created a new problem. The same dark skin that protected against too much UV now blocked too little. And UV radiation, for all its dangers, is also essential. It is the primary trigger for the synthesis of vitamin D in the skin. Without adequate UV exposure, without adequate vitamin D, bones weaken, immune systems falter, reproductive systems struggle. Rickets, the disease caused by severe vitamin D deficiency, deforms the pelvis in ways that make childbirth dangerous or impossible. In the low-light environments of Northern Europe and Northern Asia, dark skin became a liability. Not immediately, not dramatically, but over generations, individuals with slightly lighter skin had slightly better vitamin D synthesis, slightly better bone health, slightly better reproductive outcomes. The pressure was gentle but consistent, and over thousands of years, it was decisive. Consider what this means. The same sun that made dark skin essential in Africa made it costly in the north. The same pigment that was a shield at the equator became a barrier at high latitudes, blocking the very radiation that the body needed to build bone and support immune function. Evolution does not anticipate this kind of reversal. It cannot see ahead. It can only respond to the present moment, the present environment, the present pressure. And the present pressure in the grey winters of Northern Europe was relentless. Generation after generation, the individuals with slightly lighter skin had slightly better outcomes. The selection was not dramatic. It was quiet, but quiet selection, sustained over thousands of generations, moves mountains. Skin lightened. The mutations that reduce eumelanin production spread through northern populations because in low UV environments, they were not a disadvantage. They were, in the specific currency of vitamin D synthesis and reproductive success, an advantage. And this is where MC1R enters the story in a new way, because some of the mutations that lighten skin are the same mutations that, in certain combinations, produce red hair. The earliest red hair in Europe is not as old as you might expect. For a long time, the assumption was that red hair had been in Europe since the first modern humans arrived, perhaps 50,000 years ago. But ancient DNA analysis, which has transformed our understanding of European prehistory in the last decade, tells a more complicated story. The oldest confirmed genetic evidence of MC1R variants associated with red hair in Europe dates to around 10 to 12,000 years ago, in populations that were moving into Europe as the last ice age ended. These were not the first Europeans. They were part of a later wave. Hunter-gatherers who had been living in the southern refugia during the glacial maximum and were now expanding northward as the ice retreated. And here is where the story becomes genuinely strange, because the populations that carried the highest frequencies of most MC1R variants were not spread evenly across Europe. They clustered. They concentrated in specific regions, particularly along the Atlantic coast, in what is now Ireland and Scotland and Wales, and the Basque country of northern Spain. These were the edges, the margins, the places where ancient populations had been pushed by successive waves of migration and had stayed isolated enough to maintain their genetic distinctiveness, isolated enough that their particular variants of MC1R reached frequencies far higher than anywhere else in the world. Consider Ireland. Roughly 10% of the Irish population has red hair. In some western counties, the figure is higher. This is not because red hair is uniquely Irish in some essential way. It is because Ireland was, for long periods of prehistory, a genetic cul-de-sac, a place where ancient populations arrived and largely stayed, where the mixing that diluted MC1R frequencies elsewhere happened more slowly, where the particular combination of genes that produces red hair accumulated over generations in a relatively closed population. The same logic applies to Scotland, to Wales, to the Basque region. These are places where ancient genetic signatures persist at unusually high frequencies, not because of some mystical connection to the land, but because of the simple mathematics of isolation and genetic drift. When a population is small and relatively closed, rare variants can reach high frequencies just by chance, a process called genetic drift. And when those variants happen to confer some advantage in the local environment, as lighter skin does in low UV regions, they can be actively selected for as well. The result is a pocket of red hair in the Atlantic fringe of Europe, a living record of ancient population movements that happened before history began. If you have your own thread to pull here, I want to hear it. Have you ever noticed patterns like this in other ancient populations? Places where a single visible trait seems to mark the edges of where one world ended and another began? Leave that in the comments. The archive grows richer when more voices add to it, but we are still only partway through the puzzle, because saying that MC1R variants spread because they lighten skin in low UV environments explains why the gene persists in carriers. It does not fully explain why it produces red hair in those who inherit two copies, or why those people have the constellation of other traits that accompany it. It does not explain the pain sensitivity, the anesthesia resistance, the particular relationship with cold and heat that redheads report. It does not explain why the same mutation that makes hair red also seems to alter the body's fundamental relationship with sensation. To understand that, we need to go deeper into what MC1R actually does and why its effects are so wide-ranging. The melanocortin system, of which MC1R is one component, is ancient, far older than mammals, far older than vertebrates. It is one of those fundamental biological systems that evolved early and then got repurposed again and again as life became more complex. In its earliest forms, it was involved in basic stress responses, in the regulation of energy and inflammation. Over hundreds of millions of years of evolution, it became embedded in systems governing pigmentation, pain perception, appetite, immune function, and more. MC1R is not just a hair color gene. It is a node in a network that touches many of the body's most fundamental processes. When you trace the evolutionary lineage of the melanocortin system, you find it reaching back to some of the earliest nervous systems in animal life. The same basic signaling logic that tells a melanocyte to produce pigment also appears in modified form in the regulation of the stress response, in the modulation of appetite, in the coordination of immune cells responding to injury. This is one of biology's most elegant and unsettling features. It does not invent new systems from scratch. It takes old systems and repurposes them, adds new connections, new layers, new functions, while keeping the ancient core intact. The melanocortin system is a palimpsest, a document written over and over on the same surface, each new layer of function added on top of the old without erasing it. When MeO-C1R is not functioning in the typical way, as in Redheads, the effects propagate through that entire network. The pain sensitivity that many Redheads report is real and measurable. Studies have consistently found that people with 2 copies of MC1R variants require more anesthesia during surgery, on average about 20% more, to achieve the same level of sedation. They report higher sensitivity to certain types of pain, particularly thermal pain, the pain of heat and cold. They are more likely to avoid dental procedures due to fear of inadequate pain control, a finding that has been replicated across multiple studies and multiple countries. This is not psychosomatic. The mechanism appears to involve the way MC1R variants affect the signaling between pain receptors in the skin and the central nervous system. The same receptor that is not properly responding to melanocyte-stimulating hormone is also involved in modulating pain signals, and when it is not functioning typically, those signals are processed differently. The world, quite literally, feels different to someone with 2 copies of MC1R variants, more intense in certain specific ways, more present. There is something philosophically interesting about this. The same mutation that makes a person more visible, that marks them with a hair color that stands out in almost any crowd, also makes them more sensitive to the physical world. As if the gene that removes one layer of protection from the outside, the eumelanin that shields skin from radiation, also removes a layer of buffering from sensation itself. As if carrying this ancient mutation means being slightly more exposed to the world in multiple directions at once. More seen, more feeling, more present to the raw signals that the environment is constantly sending. Whether that is an advantage or a disadvantage depends entirely on context. In the world of our ancestors, moving through cold northern landscapes where thermal sensitivity might mean the difference between frostbite and survival, where an acute awareness of physical sensation might sharpen the responses that keep you alive, it is possible to imagine circumstances where heightened pain sensitivity was not a liability, but an asset. Evolution does not optimize for comfort, it optimizes for reproduction. And sometimes, being more alert to the signals your body sends is exactly what a particular environment rewards. But let us step back from the biology for a moment, because the story of red hair is not only a story about genes and receptors and melanin. It is also a story about how human beings have interpreted this visible difference across thousands of years of history, and what those interpretations reveal about the cultures that made them. Because red hair has never been neutral. In almost every culture that has encountered it in significant numbers, it has been marked, noted, assigned meaning, sometimes sacred, sometimes sinister, sometimes both at once. The ancient Egyptians had complicated feelings about red hair. In Egyptian cosmology, red was the color of Set, the god of chaos, storms, and the desert. Set was not simply evil in the way that later monotheistic traditions would frame evil. He was necessary, dangerous, powerful, associated with the untamed forces that existed outside the ordered world of civilization. Red-haired individuals in ancient Egypt were sometimes associated with Set, sometimes sacrificed in ritual contexts, sometimes venerated as carrying divine power. The ambivalence is telling. Red hair was too striking to ignore and too strange to categorize comfortably, so it was assigned to the divine, to the liminal, to the space between order and chaos. Consider what that ambivalence reveals. The Egyptians were not simply afraid of red hair. They were uncertain about it. And in a culture that organized the entire cosmos into categories of order and disorder, of ma'at and chaos, uncertainty was itself a kind of power. The red-haired person could not be easily placed. They sat at the boundary, and things that sit at the boundary between categories have always carried a charge, a weight, a significance that things firmly within a category do not. The Egyptians, with their extraordinarily precise cosmological imagination, recognized this. They did not dismiss red hair as a curiosity. They built a theology around it. In ancient Greece, the associations were different but equally charged. The historian Herodotus described the Thracians, a people living north of Greece, as having red hair and grey eyes, marking them as distinctly other, as barbarians in the original Greek sense of people who spoke a different language and lived by different rules. Red hair in the Greek imagination was associated with the north, with cold, with roughness, with a kind of vital energy that was both admirable and threatening. Achilles, the greatest warrior of the Trojan War, was sometimes depicted as red-haired. So was Odysseus, in some traditions. The association of red hair with exceptional ability, with a kind of fierce vitality, runs through Greek literature and art in ways that are easy to miss if you are not looking for them. The Romans inherited and amplified these associations. Roman writers described the Germanic and Celtic peoples they encountered in northern Europe with a mixture of fear and fascination, and red hair was one of the markers they returned to again and again. Tacitus, writing about the Germanic tribes in the 1st century, noted their fierce blue eyes and reddish hair, their large frames built for attack rather than endurance, their wild courage in battle. The red hair was part of a portrait of otherness, of a kind of primal power that Roman civilization had tamed in itself, but still encountered, undomesticated, at its borders. There is something worth pausing on in the Roman response. Rome was a civilization that prided itself on order, on law, on the disciplined application of force within carefully maintained structures. The red-haired peoples at its borders represented everything that Rome had organized itself against. They were wild where Rome was ordered, passionate where Rome was calculated, fierce where Rome was strategic. And yet the Romans could not stop writing about them, could not stop returning to the image of the flame-haired warrior standing at the edge of the known world. There is admiration in those descriptions beneath the fear, a recognition of something vital and untamed that the machinery of civilization had not quite managed to extinguish. The Celts, who occupied much of Western and Northern Europe before Roman expansion, had their own relationship with red hair. In Celtic mythology and folklore, red hair was associated with the otherworld, with the She, with beings who moved between the human world and the realm of the divine or the dangerous. Red-haired characters in Irish mythology are often marked as special, set apart, carrying some quality that distinguishes them from the ordinary. This is not simply a matter of pride in a common trait. It reflects something deeper, a cultural recognition that this visible difference signals something, even if what it signals is not always clear. The medieval period in Europe is where the associations darkened most severely. In Christian Europe, red hair became entangled with a complex of negative associations that drew on much older fears and filtered them through a new theological framework. Judas Iscariot, in medieval iconography, was typically depicted as red-haired. So was Mary Magdalene, though her red hair was gradually rehabilitated as her image shifted from sinful woman to devoted follower. The association of red hair with treachery, with lust, with dangerous excess ran through medieval European culture in ways that had real consequences for real people. The witch trials of the early modern period, which reached their peak in the 16th and 17th centuries, disproportionately targeted people with physical characteristics that marked them as different, as outside the norm. Red hair was among those characteristics. In some regions of Germany and France, red hair was considered a sign of a witch's mark, evidence of a pact with the devil. The logic, if you can call it that, drew on the ancient association of red with fire, with Set, with the chaotic and the dangerous, and reframed it through the lens of Christian demonology. Being visibly different in a culture terrified of difference was dangerous. Red hair made you visible. It is worth sitting with that for a moment. The same genetic mutation that evolved in part as an adaptation to low UV environments that helped populations survive in the cold north became in those same northern populations a marker of suspicion, a reason for persecution. The gene that may have helped your ancestors survive the Ice Age also put your medieval descendants at risk of accusation. Evolution has no foresight. It cannot anticipate how a trait will be interpreted by the cultures that arise thousands of years after it spreads. It can only respond to the pressures of the moment. And the cultural pressures of the medieval period were not gentle, and yet the trait survived. Through the Egyptian associations with Set, through the Roman gaze, through the medieval witch trials, through centuries of mockery and stigma and cultural othering, the MC1R variants persisted. 80 million people alive today carry them in their expressed form. Hundreds of millions more carry them silently, recessive, waiting for the right combination to surface again in a future generation. There is something almost stubborn about this. Not in any intentional sense. Genes are not stubborn. They do not have intentions. But in the statistical sense, in the sense that a trait which has faced this much cultural pressure and maintained its frequency must be anchored by something more than chance. Something keeps the balance. Something makes the cost worth paying. Part of the answer may lie in heterozygote advantage. This is one of the most elegant concepts in population genetics, and it explains some of evolution's most persistent puzzles. A heterozygote is someone who carries one copy of a variant gene and one typical copy. In many cases, carrying one copy of a mutation that is harmful in two copies confers an actual advantage. The classic example is sickle cell anemia. Two copies of the sickle cell mutation causes a devastating blood disease, but one copy provides significant resistance to malaria. In regions where malaria is endemic, the advantage of carrying one copy outweighs the cost of occasionally producing children who inherit two copies and develop the disease. The mutation persists because the heterozygotes, the carriers, are actually better off than people with two typical copies. Could something similar be operating with MC1R? It is a genuinely open question, and researchers are actively exploring it. There is some evidence that people with one copy of MC1R variants who do not have red hair themselves may have subtly different pain processing, subtly different immune responses, subtly different skin characteristics. Whether any of these differences confer a measurable advantage in specific environments is not yet clear. The research is ongoing, the sample sizes are still growing, and the answers are not yet definitive. But consider the possibility. Consider a population of hunter-gatherers in northern Europe 10,000 years ago, moving through a landscape of forest and tundra and river valley, where the sun was low and pale for half the year. In that population, the people carrying one copy of MC1R variants had lighter skin than the average, better vitamin D synthesis, slightly stronger bones, slightly better immune function. They were not red-haired, they were simply slightly better adapted to the light. And occasionally, when two of them had children together, those children were red-haired with all the associated traits, the heightened sensitivity, the particular relationship with pain and cold, the striking appearance that marked them as different. In that world, being marked as different was not necessarily a disadvantage. In many hunter-gatherer societies, visible distinctiveness is associated with spiritual power, with special roles, with a kind of social status that can translate into reproductive success. The shaman, the healer, the seer, these are often people who are visibly set apart, whose difference is interpreted as a sign of connection to forces beyond the ordinary. If red-haired individuals in ancient northern European populations were perceived as marked as carrying some special quality, that perception could have translated into social advantages that partially offset whatever biological costs the mutation carried. This is speculation. Let me be clear about that. The social dynamics of prehistoric populations are almost impossible to reconstruct with confidence. We have bones and stones and ancient DNA, but we do not have the conversations, the rituals, the social hierarchies, the stories people told about the red-haired child born to dark-haired parents. We can only infer, and we should hold those inferences lightly. But the inference is not unreasonable, because across cultures and across centuries, red hair has consistently been assigned significance. It has never been invisible. And things that are never invisible, in small communities where everyone knows everyone, tend to be assigned roles, tend to be given meaning. And meaning, in a social species, has consequences. What we can say with more confidence is this: the MC1R variants that produce red hair have been present in European populations for at least 10,000 years, probably longer. They have maintained a consistent frequency despite whatever pressures have acted on them. And the populations that carry them at the highest frequencies are those with the deepest roots in the Atlantic fringe of Europe. The populations that experienced the most isolation, the most genetic drift, the most concentration of ancient variants that were diluted elsewhere by successive waves of migration. Those populations are themselves a kind of genetic archive. When geneticists study the Irish, or the Basque, or the Welsh, they are reading documents written in DNA, documents that record the movements and mixings and isolations of populations that lived and died thousands of years before anyone thought to write anything down. The red hair is one of the most visible entries in that archive, but it is surrounded by thousands of other entries, other variants, other traces of ancient people who left no monuments, no texts, no artifacts that have survived, but who left themselves encoded in the genomes of their descendants. There is a concept in population genetics called a founder effect. When a large population splits and a small group moves off to colonize a new territory, the genetic diversity of that small founding group is much less than the diversity of the original population. The founders carry only a subset of the variants that existed in the source population, and whatever variants they happen to carry become more common in the new population, simply because the founding group was small. Over generations, as the new population grows, those founder variants spread widely. Traits that were rare in the original population can become common in the new one, not because they are particularly useful, but because they happen to be present in the founders. Imagine a group of perhaps 200 people moving westward along the Atlantic coast of Europe 10,000 years ago, following the retreating ice, following the salmon runs and the deer herds into a landscape that had been buried under glaciers for 20,000 years and was now slowly, tentatively, becoming habitable again. 200 people, perhaps fewer, carrying in their genomes whatever variants had accumulated in the southern refugia where their ancestors had sheltered during the glacial maximum. If even 20 or 30 of those 200 people carried MC1R variants, the frequency in that founding group would be 10 to 15%, high enough that, over the generations that followed, the trait would surface regularly, high enough that it would become part of the landscape of the community, a recognizable feature, a known quantity. The Atlantic populations of Europe may be, in part, the product of founder effects operating over thousands of years. When the ice retreated after the last glacial maximum, the populations that had been sheltering in southern refugia expanded northward. The groups that moved furthest north and west into Ireland and Scotland and the Atlantic coast were small, isolated, and carried whatever genetic variants happened to be common in their founding groups. If those founding groups happened to carry MC1R variants at relatively high frequencies, those variants would have spread through the expanding population regardless of whether they were particularly advantageous. Add to this the subsequent isolation of these Atlantic populations, their relative insulation from the later waves of migration that brought new genetic material into Central and Eastern Europe, and you have the conditions for a genetic pocket to form and persist. The red hair of Ireland and Scotland is not just a biological trait. It is a geographical record, a map of ancient migration routes and population bottlenecks written in the bodies of living people. This is what makes the Redhead story so much larger than it first appears. It is not just about a hair colour. It is about the deep history of our species, about the forces that shape the distribution of genetic diversity across the globe, about what happens when small groups of people move into new environments and find that the mutations they carry, mutations that accumulated by chance or were selected for in one context, suddenly matter in new ways in a new place. Let us think about the Neanderthals for a moment, because they belong in this story too. Neanderthals were not modern humans. They were a separate species, or possibly a subspecies, depending on how you draw the taxonomic lines, that evolved in Europe and Western Asia over hundreds of thousands of years, while modern humans were evolving in Africa. They were adapted to cold, to the grey light of glacial Europe, to a world of mammoths and cave bears and long winters. And the ancient DNA evidence suggests that at least some Neanderthals had variants of MC1R that would have produced red or reddish hair, pale skin, and the associated traits. This is remarkable. It means that the connection between pale skin and red hair and cold northern environments is not something that evolved once in modern humans and spread. It evolved independently in Neanderthals, under similar selective pressures, in similar environments. Evolution found the same solution twice. Different species, different genetic backgrounds, different specific mutations, but the same general outcome: lighter pigmentation in low UV environments. The logic of vitamin D synthesis and UV exposure is so powerful, the selection pressure so consistent, that it drove parallel evolution in two different human lineages living in the same landscape. Imagine that for a moment. Two different kinds of human, separated by hundreds of thousands of years of independent evolution, arriving at the same visible solution to the same environmental problem. The pale skin, the light hair, the particular biology of the North, not because they shared a recent ancestor who had those traits, but because the landscape demanded them. Because the grey light of glacial Europe imposed the same requirements on every large-brained, upright-walking creature trying to survive within it. Evolution, working independently in two separate lineages, wrote the same answer to the same question. And then modern humans arrived in Europe and encountered Neanderthals. We know this happened. We know it because the genomes of all non-African people today contain between 1 and 4% Neanderthal DNA, the legacy of interbreeding that occurred as modern humans moved into Neanderthal territory. We carry fragments of Neanderthal genome in our cells, inherited from ancestors who mated with Neanderthals somewhere in the Middle East or Europe between 50 and 60,000 years ago. Could some of the MC1R variants in modern European populations have come from Neanderthals? This is a question researchers have explored, and the answer is nuanced. The specific MC1R variants that produce red hair in modern humans are not the same as the ones found in Neanderthal DNA. The mutations are different, even if the functional outcome, reduced eumelanin production, is similar. So modern red hair does not appear to be directly inherited from Neanderthals through interbreeding. But the broader point stands. Modern humans moving into Europe were entering an environment where Neanderthals had already evolved adaptations to low UV. They were entering a world where the selective pressure toward lighter pigmentation was real and consistent, and they were doing so carrying, in some cases, Neanderthal DNA that included genes involved in immune function, in cold adaptation, in a range of traits that helped them survive in their new environment. The Neanderthal legacy in modern human genomes is not just a curiosity. It is a toolkit, a set of adaptations that helped modern humans colonize a world their immediate ancestors had never known. The red hair that emerged in European populations over the following thousands of years was not Neanderthal red hair, but it was shaped by the same forces that had shaped Neanderthal adaptations, the same low sun, the same cold, the same relentless pressure toward vitamin D synthesis in a world where the light was never quite enough. There is something deeply moving about this, if you let yourself feel it. The idea that the visible traits of people alive today, the color of their hair, the paleness of their skin, the particular way they experience cold and pain, are echoes of ancient environments, ancient pressures, ancient encounters between species that no longer exist. That when you look at a red-haired person, you are in some sense looking at a message sent across tens of thousands of years, a message written in the language of genetics, saying, "This is what it took to survive here. This is what the light demanded." The archive of human genetics is full of messages like this. Every population on Earth carries in its genome the record of where its ancestors lived, what pressures they faced, what adaptations they developed, what other populations they encountered and mixed with. The genome is a history book, and red hair is one of its most visible chapters. But it is a chapter that most people walk past every day without reading, without recognizing the depth of what is written there in the simple fact of a color. But the story is not over. It is still being written. Because the world is changing faster than evolution can respond, and the traits that were adaptive in ancient environments are now operating in contexts their origins could not have anticipated. The pale skin that helped Northern Europeans synthesize vitamin D in low UV environments now increases their risk of skin cancer in a world where people travel freely between latitudes, where UV exposure is no longer reliably correlated with ancestry. The heightened pain sensitivity that may have been an asset in a world of physical danger and constant environmental challenge is now navigating a world of dental offices and surgical suites and chronic pain clinics. And the red hair, that most visible marker of the MC1R mutation, is navigating a world where it is simultaneously celebrated and mocked, where it is the subject of genetic research and the target of playground cruelty, where it is associated in popular culture with everything from fierce independence to comic buffoonery. The cultural meanings of red hair are still being written, still being contested, still being assigned and reassigned in ways that the gene itself knows nothing about. There is a persistent question in the popular literature about red hair, and it is worth addressing directly because it touches on something important about how we think about genetic traits and their futures. The question is whether red hair is going extinct. You may have seen the headlines. Geneticists warn that red hair could disappear within centuries. Climate change threatens redheads. The last redhead will be born in the year such and such. These headlines are almost entirely without scientific foundation, and understanding why they are wrong tells you something important about how genetics actually works. Red hair is recessive. This means that the MC1R variants that produce it are far more common in the population than the frequency of red hair itself would suggest. For every person with red hair, there are many more people carrying one copy of MC1R variants who have no red hair at all. These carriers are invisible to the casual observer. You cannot look at someone with brown hair and know whether they carry an MC1R variant. But statistically, in a population where 1 to 2% of people have red hair, somewhere between 20 and 40% of people may be carriers, depending on the specific population. For red hair to go extinct, MC1R variants would have to be eliminated from the population entirely, not just from the people who express them visibly, but from all the carriers as well. This would require sustained, powerful selection against the gene, strong enough to overcome the protection that recessive inheritance provides. There is no such selection pressure operating. In fact, in a world where vitamin D deficiency is a global health concern, where populations are mixing across latitudes in ways that change the UV exposure of individuals relative to their ancestral adaptations, the MC1R variants may be under less negative selection than at any point in human history. The frequency of red hair may change over time as populations mix, and the isolated Atlantic populations that carry the highest frequencies of MC1R variants blend with other groups, but the gene itself will persist. It will continue to surface in unexpected places, in unexpected generations, a surprise in a family where no one has had red hair for decades, a reminder that the genome carries more history than any single generation can express. There is a term in genetics for this kind of persistence: cryptic genetic variation. Variants that are present in a population but not expressed, hidden in heterozygotes, waiting for the right combination to surface. The human genome is full of cryptic variation, full of ancient mutations that accumulated over hundreds of thousands of years of evolution and are now maintained at low frequencies, occasionally surfacing, occasionally disappearing, never quite going away. Red hair is one of the most visible examples of this phenomenon, but it is surrounded by thousands of invisible ones, ancient variants that we carry without knowing, that shape our biology in ways we are only beginning to understand. The science of ancient DNA has transformed our ability to read this cryptic variation. In the last decade, researchers have extracted and sequenced DNA from thousands of ancient individuals, from bones and teeth preserved in archaeological sites across Europe and Asia and the Americas. And the picture that has emerged is one of extraordinary complexity and movement. The people who live in any given region today are almost never the direct descendants of the people who lived there 10,000 years ago. Europe has been repopulated multiple times by hunter-gatherers after the Ice Age, by farmers from Anatolia in the Neolithic, by steppe pastoralists in the Bronze Age, each wave bringing new genetic material, new variants, new combinations that mixed with what was already there. The red hair that concentrates in the Atlantic fringe of Europe today is partly a record of what survived these successive waves of migration. The hunter-gatherers who carried high frequencies of MC1R variants were largely replaced by incoming farmers in most of Europe, their genes diluted by the much larger populations of agriculturalists who spread from the Middle East. But in the far west, in Ireland and Scotland and Wales, the farming revolution arrived later and less completely. The ancient hunter-gatherer genetics persisted there at higher frequencies than almost anywhere else in Europe. And with those genetics came the MC1R variants, the pale skin, the red hair, the freckles, the particular biology of the Atlantic fringe. When you look at the distribution of red hair in Europe today, you are looking at a map of ancient survivals. You are seeing where the hunter-gatherers held on, where the farmers' expansion slowed or stopped, where the Bronze Age migrations had less transformative impact. The red hair is a signal in the noise of history, a marker that points back to a world that was already ancient when the pyramids were built. It is a data point in a map that was drawn in flesh and blood and bone, across thousands of years of movement and settlement and displacement, by people who had no idea they were drawing anything at all. What other signals like this have you noticed hiding in plain sight, in language, in place names, in the faces of people from particular regions of the world? If something has always struck you as a living trace of a forgotten history, I would genuinely like to read it. Leave it in the comments. And this brings us back to the question we started with. Why do redheads exist? Why does this mutation persist, in defiance of the simple story of natural selection that says costly traits disappear? The answer is not simple. It is layered, like the archive itself, with each layer revealing something that complicates and enriches what came before. Redheads exist partly because the MC1R variants that produce red hair also lighten skin, and lighter skin was adaptive in low UV environments. The gene was selected for in northern populations not because of the red hair it occasionally produced, but because of the vitamin D benefits it conferred on the many more carriers who never expressed it visibly. Redheads exist partly because recessive inheritance protects genes from natural selection, allowing variants to hide in carriers across generations, maintaining their frequency in the population even when they are not being expressed. Redheads exist partly because of genetic drift, because the small founding populations that colonized the Atlantic fringe of Border Europe happened to carry MC1R variants at relatively high frequencies, and those frequencies were amplified by isolation and the founder effect. Redheads exist partly because of the Neanderthal shadow, because the selective pressures that drove Neanderthals toward lighter pigmentation in glacial Europe were the same pressures that acted on modern humans as they moved into the same environments. And those pressures were real and consistent and powerful. And redheads exist partly because evolution is not the ruthless optimizer we sometimes imagine it to be. It is a process that works with what it has, that maintains variation, because variation is the raw material of adaptation, that tolerates costs in the short term because the long-term environment is unpredictable. A trait that is costly today might be essential tomorrow if the environment changes, if a new disease arrives, if the climate shifts, if a new set of pressures emerges that the current generation cannot anticipate. Maintaining genetic variation, even variation that seems costly, is a kind of bet hedging, a way of keeping options open in a world that never stays the same. Perhaps that is the deepest lesson in the Redhead story. Not that evolution is wise, because it is not wise. It has no mind, no foresight, no intention. But that the process of evolution, precisely because it has no foresight, tends to be conservative about eliminating variation. Variation is the hedge against an uncertain future, and the future is always uncertain. The ice ages that shaped the selective pressures driving MC1R frequencies in European populations were not predictable events. The populations that survived them did so not because they had planned for them, but because they happened to carry in their genomes the variation that the new environment rewarded. The variation that looked costly before the ice turned out to be essential after it arrived. The 80 million redheads alive today are not evolutionary mistakes. They are not vestiges of a failed experiment. They are the visible expression of a genetic variant that has been maintained in human populations for tens of thousands of years by forces that are still not fully understood, that has shaped the biology of hundreds of millions of carriers who will never have red hair themselves, and that carries in its distribution the record of ancient migrations and isolations and encounters that shape the world we live in. They are, in the language of the archive, primary sources, living documents, genetic testimonies to a past that is otherwise almost entirely silent. There is one more thread to follow before we let this story settle into the quiet. It is the thread that connects the biology to the experience, the genetics to the life that is actually lived in a body that carries this particular combination of ancient mutations. People with red hair report, consistently and across cultures and centuries, a sense of being marked, of being visible in ways that other people are not, of navigating a world that notices them, that assigns them meaning, that projects onto them a range of qualities: fiery temper, passionate nature, magical power, dangerous difference, that have nothing to do with who they actually are and everything to do with the long cultural history of this visible trait. This experience of being marked, of being a visible carrier of ancient variation, is in some ways the most human part of the story, because we are the only species that assigns cultural meaning to genetic variation. We are the only species that looks at the colour of a person's hair and constructs a mythology around it, that writes the red-haired witch and the red-haired warrior and the red-haired fool and the red-haired saint. We are the only species for whom a mutation in a pigmentation gene becomes a social identity, a cultural category, a source of pride or shame or fascination. The gene does not know any of this. The MC1R receptor on chromosome 16 does not know that it is the subject of myth and legend and scientific research and playground teasing. It simply does what it does, disrupting the signal that would otherwise produce eumelanin, allowing pheomelanin to fill the space, sending its effects rippling through the melanocortin system into pain perception and inflammation, and all the other processes where this ancient signaling network has its fingers. But the person who carries two copies of this mutation lives in a world that has been noticing and interpreting and mythologizing their hair for as long as there have been people to notice it. They carry not just the gene, but the accumulated weight of all the meanings that have been attached to it, the set associations and the witch trial fears and the Celtic otherworld connections and the Roman observations about barbarian vitality and the modern research papers about anesthesia requirements. They carry all of that, whether they know it or not, in the simple fact of their visible difference. There is something quietly extraordinary about this, about the way a single mutation, a single letter change in a single gene can connect a living person to the deepest layers of human history, can make them, in some sense, a walking archive, a genetic ghost who is also very much alive, carrying the past in their cells while navigating a present that is still as it has always been, trying to figure out what to make of them. The archive never closes. The files are never complete. Every generation adds new evidence, new interpretations, new layers of meaning to stories that began before writing existed, before cities existed, before the concept of history itself had been invented. The red hair of the Atlantic Fringe, the pale skin of the northern populations, the heightened sensitivity of people who carry 2 copies of an ancient mutation. All of these are chapters in a story that is still being written, still being read, still being understood. And perhaps that is the right note to end on. Not resolution, but continuation. Not the closing of the archive, but the recognition that it is always open, always receiving new material, always inviting the patient reader to come back and look again, to find in the familiar something that was not visible before. If this one found you on a sleepless night, consider returning to it on the next one. The layers tend to reveal themselves differently in the dark, and if someone in your life carries a quiet curiosity about where they come from or why their body works the way it does, this is the kind of story worth passing along. Sharing these hidden histories is one of the quieter ways we preserve things that deserve to be remembered, and there is something meaningful about connecting a fellow seeker to a question they did not know they were waiting for. 80 million redheads. By every rule of natural selection, the number should be 0. And yet here they are. Here they have always been, carrying in their visible difference the record of ice ages and migrations and ancient encounters, the record of what it took to survive in a world of pale light and long winters, the record of the small groups who moved to the edges of the known world and stayed there, and whose descendants are still, 10,000 years later, carrying the genetic signature of that ancient choice. The mutation persists, the archive holds, and somewhere tonight, in the Atlantic rain, in the grey light of a northern morning, in the warm interior of a house where a child with copper hair is sleeping, the ancient variant is quietly doing what it has always done, filtering the light, shaping the sensation, connecting the living to the long, patient, almost unimaginably deep story of what we are and where we came from. Sleep well, the archive will be here when you wake. The hunter-gatherers who carried these ancient variants were not the only ones leaving traces that still reach us today. At Göbekli Tepe, people who predate every civilization we thought we knew were already building something that should not have existed. What they left behind changes the entire story of what early humans were capable of, and that file is already open and waiting for you.